And the date, I cannot change. This date cannot be changed by instructors or student. This date is set by the university. So we cannot change this date at all, even if I don't like it. I don't like this date at all, but it's not up to us. And it is covering 1 through 9, and I will show you the practice test problems, and you can study those practice problems. And I realized that some of you have hard time proving proof problems. I mean, showing proof problems. So I want to lessen the proof problems, like maybe about 20% proof problems, and 80% calculation problems, and so on. About the percentage I will mention later. And there will be only one more homework set, that is Chapter 9. So it will be collected later, like May 7th. This is the final homework. And we will use 2 days to review for the final. We can study Chapter 1 through 9 for the final, and then I will post the practice test before May 7th. But it could be way earlier than May 7th. In any case, we will prepare for the final exam. And if you have a question about, I will not mention about exam 2 now, because online students need to take the exam 2 maybe by the end of this week. So I don't want to reveal any secret about the exam 2. But next week you can ask anything about exam 2. And we want to focus on final exam today. If you have a question about the final exam, ask me. This is only one more chapter. And then I will use practice 1, practice 2, and the new practice for Chapter 9. And then create a new set of practice problems and post it before May 7th. Then you can study practice problems before May 7th. And I will reduce the number of problems asking proofs, because I found that some of you had hard time proving things. In any case,
on the exam, are you going to have about the same number of problems, 5, or are you going to increase it?
because we doubled the hour of exam, the problem number can be doubled, but I will check how long it takes to solve the problem. And as I mentioned before, for the problem such as Chinese remainder problem, you don't have to write the full solution like this. You can just leave the expression alone. Then this can give you almost a full credit, even if you couldn't get the right side, because the only step required there is addition and then division. But in any case, I will solve the problems myself and then check the number of problems. So roughly 7 through 12 problems are possible. And among these, I may ask 1 or 2 proof problems. So this is the rough estimate. But in any case, about the time we begin to review, like May 7th, we will see how many proof problems are there and so on. Just a moment. In the past, last time I mentioned that there are 3 proof problems, right? I mentioned. But I found that because of the hard time that you had, I want to reduce the number of proof problems. I thought proof problems can be easier because you can just write a few lines. I tried to find the shortest proof problems. But my estimate might be incorrect, or there might be discrepancy. Yes? No, if we allow calculators, then it becomes the calculator contest. Someone has state-of-the-art calculator, someone cannot afford, and it is not a brain activity problem, it becomes calculator activity problem. So I want to reduce the size of the numbers next time so that no calculator doesn't cause any problem. For instance, even this time, I wanted to check whether you can really multiply numbers, but only one problem. It was limited to only one problem, and next time, even that might be limited. Any other questions about the final? Because final exam is very close. It's a good idea to have the figure about the final exam and how to succeed. And as I mentioned before, if your grades are good, then it's good. But if your grades are bad, then you can take the final exam seriously and then override all bad exams by using final, right? So try very hard in case that you need to pass the course. Yes?
Now, you said that if we do better on the second exam, it overrides our first exam?
Right. Always later exams can override all your exams, assuming that you submit enough homework problems. So assume that you get the nice grade on the final. Then, for instance, you get like 80 here, and then 70 here, and then you get 90 here. Then this 90 can override these, and then you can get the grade according to this number, and then homework submission.
What if your first test was good, second test was bad, and then it's good on the final? Does it just replace your second test? Like if you had 90, 50, 80.
So 90, 50, 80, then 80 can override this one and then replace this by 80. Any other questions? You don't go reverse way. In other words, like getting 100 on the first exam doesn't mean you can override all bad exam in the future, the other way. But if you get nice score on the final, and then you can get these things, if you submit enough homework problems. If you didn't, then submit homework problems as soon as possible before the grader gives up. If the grader gives up, then how can I know how many homework problems you submit? I do not know. So in case that you need to pass this course badly, then take the final exam seriously. And as I mentioned before, it will cover only 9 chapters, 1 through 9, right? And then we will solve plenty of practice problems before the exam. No questions about the final exam? Because unfortunately, if it's not an online exam course, I might answer all the questions about exam 2 right now. But because it's online exam, some students need to take the exam today or tomorrow and so on, so I don't have to reveal the secret. Then let's begin to cover the final chapter of this course. And after this chapter is covered, I will mention the other chapters briefly, even though they are not questioned on the final exam. On the syllabus that you saw, I mentioned that we will cover, for instance, chapter 12, 13, 15, 16, and so on. But because of lack of time, we cannot cover all those chapters seriously. So I will mention the crux of those chapters after finishing chapter 9 completely, because chapter 9 is important for the final exam. I will focus on chapter 9. And chapter 9 covers this problem. Chapter 9 covers this problem. Is there a solution for a specific number given in the box? If, for instance, 5 is given, is there a solution or not? So this is the key to chapter 9. So in chapter 9, we handle this problem in various sections and various problems and various theorems. The key is having or finding. Finding is not our major concern. Checking whether it has a solution or not is our major concern. For instance, with mod 3, can any of you find the solution to this? With mod 3, can any of you here find the solution to this? Excuse me? I mean, x, what should be x?
Oh,
What should be x? with mod 7, there are 3 possible numbers. With mod 7, there are 3 possible numbers, and we plug it in. 0 squared is 0, and then 0 is not congruent to 2, so disqualified. 1 squared is 1, disqualified. 2 squared is 4. 4 o'clock is the same as 1 o'clock, so none. In other words, we tried everything and couldn't find a solution. In other words, this problem doesn't have a solution. So some problem has a solution, some problem doesn't have a solution. So in this chapter, our major concern is checking whether it has a solution or not. So superficially, it's a very trivial chapter. So this is the crux, main theme of this chapter. So you now know the situation. X squared equals something, then does it have a solution or not? This is the major theme. But to solve this matter, mathematicians developed many tools. Those tools might be tough to study. But the problem itself is very plain, right? In other words, you have an equation, x squared equals 2. Then does it have a solution or not? As you can see, with mod 3, it's impossible. It doesn't have a solution with mod 3. So instead of using small number, I will ask you to check these 2 problems. With mod 7, x squared equals, for instance, 2, 3. So please check whether the top one has a solution, and then check the second one has a solution. So please check these 2 cases on your own. Then you will see why mathematicians try this hard to develop some theorem determining the existence of solution. As soon as you've determined it, tell me, solution exists or not? Yes? Solution exists or not? No? So to do it, I will square 0 up to 6 squared, right? Because mod 7, right? 0 squared is 0. 1 squared is 1, 2 squared is 4, 3 squared is 9, 9 is 2, right? 4 squared is 16, 16 is 2, and then 5 squared is, and then 6 squared is 1. And take a look. Take a look. Can you recognize? So if we exclude trivial case, right? This 0 is trivial case. We can break this up into half, and then consider just a half. That is good enough, right? Consider just a half. That is good enough. So in this sense, this 2 has a solution, right? Because of this. In other words, what is the solution? 3, right? 3 is the solution to this equation. But 3 has no solution, right? There is no 3 at the bottom line, right? If you don't understand, ask me. So from this point on, let's not worry about this trivial case. In other words, in our consideration, 0 or some number congruent to 0 will be completely ignored, right? Something that is congruent to 0 is useless to consider because 0 squared is always 0, and it doesn't give us any useful result. So final time, this is the final time checking it. Mod 11. So please find whether this has a solution or not by using the similar method that I mentioned. And do not consider 0 anymore from this point on. So 3 has a solution because of this, right? That solution is what? Y, right? So 5 squared is congruent to 3. So it has a solution x. X is equal to 5, right? In other words, x is equal to 5. So the second line, this portion has a solution, but this doesn't have a solution. So no solution. So do you see the point? Depending on modulus or the number, sometimes solution exists, sometimes solution does not exist. So we care about this existence in this chapter. If you don't understand, ask me. Then take a look. First of all, if solution exists for a number here, then we call the number, I will write it in the following column, quadratic residue. If solution does not exist, right, then it's called quadratic non-residue. Quadratic non-residue. So if solution to the problem exists, then the numbers on the right side is called quadratic residues. And if the solution does not exist, then it's called quadratic non-residues. So let's check what are quadratic residues for 7. For 7, quadratic residues are 1, 4, right? And then 3 squared is 2. So these are quadratic residues. And with 11, quadratic residues are 1, 4, 9, and then 4 squared is 16. 16 is congruent to 5. And then 5 squared 25 is congruent to 3. So these are quadratic residues. That means the complement of this set, that is, for instance, 3, 5, 6, right? 3, 5, 6 are quadratic non-residues. So these are quadratic residues, and quadratic non-residues are complement of this. So I don't want to write the quadratic non-residue. Just residue will give you the clue. So these numbers are quadratic residues of 7. These numbers are quadratic residues of 11. So please check and ask question. If you don't, then I will begin to tackle this problem mathematically. I just showed you the idea or definition part, but after this, I will begin to tackle the problem mathematically. But before tackling the problem, you should have a clear picture about the problem, right? What are we handling? We are handling the existence of quadratic residue or not, right? Solution or not. So checking the existence of solution means checking whether it's a quadratic residue or non-residue, right? Do you see the equivalence? checking whether solution exists or not is equivalent to checking whether the number is a quadratic residue or a quadratic non-residue. In other words, give me two numbers, one prime number that is modulus, and one number that you want to check. For instance, modulus is 37. Give me a number. For instance, 17. Is 17 a quadratic residue? That kind of problem, right? So in this chapter, you will be questioned to check whether it's a residue or not. Then you may think, oh, I don't have to worry about anything. I will just guess on the exam. It's 50-50 chance, right? I can say 50-50. But unfortunately, the final exam, doesn't just rely on the answer alone. I want to see the steps, or I want to see the theorem behind those steps. So we don't know whether it's residue or not. 50-50 chance, right? Yes or no, right? But unfortunately, that's not the question I will ask. First of all, to check it, I will, instead of hand calculation, I will use MATLAB and then check all numbers up to the half, right? Half, right? P minus 1 over 2. Half doesn't mean just a half, but a little bit less than half. So let's do it. What I want to do is calculation of power, not the power mod, but x squared. So I squared mod, and mod is, in this case, n. So what I want to do is doing the calculation for 37. So I will print out these numbers up to almost a half, right? Do you see? I will print out I and mod this number up to this number. So let's do it. Then as you can see, these are quadratic residues. These are quadratic residues. 1, 4, 9, 16. Obvious, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So up to some point it's trivial. But once it passes the modulus, then it's not trivial anymore. 25, even 36 is okay, right? Even 36. So up to this point, it's something squared. It's trivial. But if it is 7 squared, 49. 49 mod 37 is 12. So it suddenly become tough, right? It suddenly become tough. 27, 7, 26, 10, 33, 21, 11, and then 3, and then finally 34. And then 30, and then 28. 28. Did you see 17 anywhere? Oh, if I omit the left side, you can handle the problem easy. I will omit this portion so that you can really see the numbers related. So check whether you see 17 here or not. If you see 17, tell me. Do you see 17? No, right? We don't see 17. So 17 is quadratic non-residue because of this search. I didn't use any mathematical technique at all. So it's quadratic non-residue. Right? 17 is not quadratic residue, as you saw. I didn't use any mathematical theorem or technique to determine it. I just searched the quadratic residue and didn't find 17. So one more brute force method. But on the exam, you cannot rely on this technique either, because I will use 3-digit numbers, which is pretty large. For instance, 127 or 927, 928 or something. Then if you do hand calculation from, I should have used prime, but I didn't know the prime number, so I will just write the number like this. I do not know whether it's prime, or I will pick some prime of 3-digit like this. Then if you rely on this brute force technique, then you should investigate about 460 numbers, right? More than 460 numbers you should investigate. Then you will consume all the exam time, and then may not even get the correct solution because of possible error in like 200th position, right? So you need to know the theorem to determine it, not brute force calculation, but let's consider it anyway. For instance, if we have like is prime 937 is prime? Yes, it's prime, right? If it is 937, what happens? 937, and then I will ask whether 17 is quadratic residue or not. Do you understand what I mean? Then if you rely on brute force calculation, all you need to do is doing this calculation, and let's do it. Then these are the numbers that you should investigate. But can you do it? Like 460 numbers without any mistake? You must check whether 17 is found in this set. If you find 17, tell me. I want to show this to online students too. So as you can see, up to some point is straightforward, but after that, as you can see, it can go very wild, right? You don't know what can happen. 400 to 500, still no 17, right? You don't see 17 at all. Have you seen 17? To 73. So I'm showing you why mathematicians develop so many theorems instead of relying on the definition like this. Because brute force technique is very difficult. Take a look. So we don't find that number. Even if we did, can we rely on our finding? We may make a mistake, right? We may make a mistake, right? We might make a mistake somewhere and then ignore the problem or ignore the number and so on. So as you can see, almost impossible even with the computer, right? Even with the computer, it's almost very difficult, right? So I do not know whether it's quadratic residue or not. But once you study section 3, section 9.3, you will easily determine this kind of number. Using section 3, you can easily determine this kind of number. But if you have a question about the topic itself or the method that I mentioned, ask me. If you don't, then mathematical approach will be studied instead of like brute force observation, right, or findings. Then let's begin. Let's begin in the new page, right? New page, clean page. So, first thing first. Euler developed very, very smart idea that is used not for calculation, but for theory. Then why is it important? Because with Euler's idea, we developed a theory, and that theory gives us the better approach to handle the problem such as the previous one. Roughly speaking, what you do is reversing it with appropriate power. This kind of theory will be studied. Once you reverse it, then the top portion can be divided by 17, and the only remainder should be considered. In other words, if you divide this by 17, then about 5, 6 is too much, right? 6 might work, right? No, 6 is too much. 5 is good. And then 87, then still 5, right? 85. The remainder is 2, right? So 97 is... Sorry. I used a symbol that I didn't even explain. Sorry, I made a mistake. But in any case, we learn about the symbol later, and then this type of thing, and then we can do the calculation later. But in any case, this Euler's theorem gives us the clue about this kind of approach that we will study in section 3. As you can see, brute force calculation, even with the computer, was tough to find whether this is quadratic residue or non-residue, right? To determine whether this is residue or non-residue. But with this kind of approach, by just mere hand calculation, we can easily determine whether it's a residue or not. This kind of approach will be studied later, but I was a little bit ahead because I didn't even explain the symbol. So reserve this thing for the future, and then later we will return back to this type of approach. But let's cover what Euler's criterion is. Euler said, if the number, so in other words, I use 17, right? If 17 to the power of 937 over 1 is congruent to 1, then it's residue. If not, then non-residue. Do you get the idea? Do you get the idea of Euler's criterion? Instead of searching through the numbers or something, Euler developed some theoretical approach. Of course, this itself is tough to calculate because it requires 17 to the power of almost 400, right? Almost 500. So it's not easy to calculate this number, but at least theoretically, he gives us the clue to check whether 17 is quadratic residue or not. With mod 937, he developed this kind of approach. Then I developed this before, so let's do it. 17, and then 937 minus 1 is 936, then 468, right? Right? So Euler criterion, use that number and then modulus to check whether it is congruent to 1 or not. If it is congruent to 1, then it's ready. So let's check it. So what I want to do is 17 to the power of 469 mod lines 37, right? So let's do it. Power mod 17, and then n minus 1 over 2 power, right? And then mod n. Do you see it? Right? Mod n and then n minus 1 over 2 power. Then it will give us 1 or not. It gave us 1. Do you see? In other words, if it gives 1, then 17 is quadratic residue. Why? Because 17 to the power of this number become 1. Then let's check 18. What if we give 18? Is 18 quadratic residue? So I will pause and then check 18 with computer. It's not hand calculation. Because it's not hand calculation, Euler's criterion cannot be used to solve a problem. In other words, you should study all the way to the end to learn good technique. If you just stop studying after Euler criterion on the exam, how can you calculate this kind of power? Impossible, right? So if you completely understand this situation, I will run for 18. In other words, is 18 quadratic residue? How can you check it? 18 to the power of 468. I will do it. 18, right? Wow, 18 is also quadratic residue. 18 is quadratic residue because of Euler's criterion, right? Quadratic residue. You may pick any number between 1 and 937. I will run your case until we can find quadratic non-residue. So pick any number in between. 112 was chosen. Then what should we do? 112 to the power of like 937 over 1 or 120, 12, 468, right? We should do this to check it. So I will do this. So 112 will be used here. Suddenly, it's not anymore, right? So this is not congruent to 1 anymore. So what does this say? It is a quadratic non-residue, right? So do you see the point? What you are handling is not trivial addition or multiplication. No. What you are handling is a big problem. Whether we can find this thing. Where do we use this? Cryptography. One more example may satisfy you completely. So you may pick any number in between so that we can check whether it's a quadratic residue or not. So pick final number. Final number. If you don't, I will begin to write 400. So 413 was chosen. Then let's finalize it. 413. 1, right? So it's a quadratic residue. So in this chapter, we determine whether the given number is quadratic residue or non-residue using theory, but we need to develop theory. So I will write the theorem in abstract form. So Euler's criterion is this. If a to the power of this is congruent to 1, then a is quadratic residue, and the other direction is the same. If a is quadratic residue, then a to the power of this is 1, so I will delete if, because it is bidirectional. If this happens, then it's quadratic residue. If this happens, this equality holds. So please browse the criteria and check with the examples that I gave you. No questions about the criterion itself? Then proof. Of course, you hate proofs, right? So I decided not to ask many proofs on the final, maybe 1 or 2, that's it. So I felt I asked pretty short proofs on the exam. So let's do it. What direction do you think is easier? Up to down, down to up. What direction do you think is easier? Always some direction is easier than the other. What direction do you think is easier? Up direction is easier. Why? Because if A is quadratic residue, right? If A is quadratic residue, then there is a number satisfying this. Do you see it? If A is a quadratic residue, then there is some X satisfying this. Do you see? A is a quadratic, then some number. This is the definition of quadratic residue. So, for instance, this number could be called, you may pick any name. What do you like? I chose already alpha, right? There is some number alpha, which gives us this result. Then, A to the power of this, I want to check this part, right? I want to check whether this is 1 or not, right? I want to check whether this is 1 or not. But we have alpha, right? Alpha squared is A, right? A is equal to alpha squared, so we get this result. And then we get this result. And then this should be equal to what? 1 by what theorem? Fermat's theorem, right? Fermat's theorem says this. If we multiply any number, p minus 1 times for prime p, then it is 1. This is Fermat's theorem. Or a special case of Euler's theorem. So this direction is easier. In other words, if it's a quadratic residue, by definition, quadratic residue means there is a number satisfying it. Then this a to the power of p minus 1 over 2 is equal to this, and then it is eventually congruent to 1 by Fermat. So this direction is easier. The other direction is tougher. So I will solve the other direction, unless you have a question about the easier direction. Do you have any question about the easier direction? Quadratic residue means power, half power. I will call it half power, even though it's not exactly half, but half power gives you the clue, right? The idea. So about the half power will be enough, right? So the other direction, in other words, if half power to the number is 1, then A is quadratic residue is the one that I want to prove, right? Half is not exactly half, but half is p minus 1 over 2. This is called half for just abbreviation or for easier description. H is exactly almost half, right? Almost half, but because p is odd over 2 is not an integer, so almost half, right? So if you have A, the number A, and that half power, then it should be equal to what? It should be quadratic residue. So how can you prove it? We use, so this might be the reason why proof is usually tougher. To prove it, it's not just calculation or applying theorem. We need to know a few stuff. First of all, primitive root. When it's a prime, right? Because p is prime, there is a primitive root, say r, right? Do you see it? When we have a prime number, there is a primitive root. How many primitive roots are there for a certain prime p? How many? Yeah, phi minus, right? Phi of p, yeah. Phi of p minus 1, right? So there are phi of p, right? Prime numbers, and then phi of p minus 1. And then we don't know how many numbers here, because p minus 1 is not prime anymore. We don't know how many are there. But theoretically we know, right? So at least we pick one case. Then I will ask a question. What is the smallest number? What is the smallest power giving this relation? First, smallest power giving this relation is one number. Other than 0. Other than 0. Any positive integer. Any positive integer. Find any positive integer giving this relation when r is a primitive root. By definition of the primitive root, it should be achieved at what power? Phi of p, right? Or p minus 1, right? phi of p, or generally p minus 1. In other words, this is done only at p minus 1. It doesn't happen before. In other words, 1 through p minus 2, it doesn't happen. But it happens only when it's p minus 1. It's the definition of the primitive root, right? If you have a question about this definition, ask me. So this could be the reason why you had a hard time proving something. When you want to prove one, then you know the previous step, and then previous step requires some knowledge about other than it is the accumulation, right, as I mentioned before. So I didn't try to make the exam hard, but the material becomes harder and harder and harder because of accumulation. But in any case, if you don't have any question about this, then I will continue. But if you still have a question about this, ask me. Then by the theorem, r squared, r cubed up to r to the power of p minus 1 are all relatively prime, right? Right? They are all different residues. Then how many numbers can you find? In this set, 1 through p minus first power, how many numbers can you count? P minus 1 numbers you can count, right? So it essentially covers all possible numbers in the set, all non-trivial numbers. Non-trivial number is 0, right? So it covers all non-trivial numbers. So some number here should be A. A is given by the problem, right? A is given by the problem. But this number should be somewhere because this set covers the whole set of numbers. Whole set of numbers which is non-trivial, right? Do you understand what I mean? Or if you don't, then I will explain this slowly. So because of this reason, we can call the power r to the power of some number. You may pick any letter. Beta, any letter is okay. Beta, right? R to the beta is congruent to A. R to the power of beta is congruent to A mod P. Why? Because these are set of numbers which are relatively prime, right? And then there are total P minus 1 numbers, but the set itself has only P minus 1 numbers. In other words, as sets, they are the same, right? As sets. So that A, that number given by the problem, that A, right, given by the problem, should be some number in between, right? So let's call that number r to the power of beta. So as you can see, proof is tough, right? Then let's do it. What is the condition and what is the goal? The condition is this. Condition is this, right? This is the condition, and I want to prove that A is quadratic residue. Do you see it? This is the condition, and so I will use the condition. So condition is A to the power of P minus 1 over 2 is congruent to 1. This is the condition given by the problem, right? Or the statement. So this is the condition. Then we can replace this by, r to the power of beta. R to the power of beta, and this one. Then, as you can see, r to the power of beta times p minus 1 over 2 achieves this. Because r is primitive root, what power achieves this? What power achieves this? Any power? In other words, this is achieved earliest when the power is p minus 1. This is the earliest time possible, right? Then this is achieved when generally some number multiplied by p minus 1, right? Because this is 1. If we multiply many times, it's possible. So in other words, we can achieve this fact when this power is nothing but some number times p minus 1. If you don't understand, ask. In other words, for less power than p minus 1, it can never be 1, right? R is never become 1. That's the definition of older, and that's the definition of primitive root. Primitive root achieves this only when it is p minus 1, and any smaller number, then this one cannot achieve it. This is the definition of the primitive root, and as you can see, we achieved this by this power, right? We achieved this by this power, then this is achieved only when it's p minus 1 multiplied by some number. So because of this reason, this number should divide this number, or I will write it, p minus 1 should divide this power that achieved this statement, right? But if you don't understand, ask me. It's a little bit theoretical, but not very tough. So please check it and ask. Then as you can see, p minus 1 divides this number, but if beta is odd number, beta is an odd number, can it divide odd over 2 multiplied by p minus? It's impossible, right? Right? This is impossible. Because p minus 1 divides p minus 1. But if it's odd over 2, then odd over 2 cannot be divided. So it cannot be odd. So beta is even. Because of this fact, beta should be even. So let's write beta. The beta equals like 2 times some number. You may pick any letter. Gamma, right? 2 times gamma. Then let's return back to the statement. I said A is congruent, A is equal to, A is congruent to R to the power of beta. But beta equals what? Beta equals 2 gamma, right? Then I can write it this way. Oh, R to the power of gamma squared. Then done. Why? Because R to the power of gamma squared is A. This is the solution to the problem, right? This is x. X squared is A is achieved. So because of this reason, A is quadratic residue. But as you can see, proof is way harder than the statement itself. In many cases, it's the same. Take a look at Fermat's-Little theorem. Fermat's-Little theorem is very trivial to state. But proving it requires some idea. It's the short idea, but some idea. But as you can see, once it comes to this level, even though statement is simple, proof is not simple. Take a look. So statement is this. If A to the power of half is 1, right? A to the power of half of the power of this number is 1, then A is quadratic residue. Prove it. Then you need all these steps to complete the proof. All these steps. So please browse your note and check whether you completely understand these steps or not, because this is the crucial part in determining the existence of solution, or in determining whether it's quadratic residue or non-residue. Then, what happened when if? So the next question is this. What if A to the power of half, right? Half, or I will use half. That makes it the understanding easier. Half is, in other words, I mentioned that if this half power gives us 1, then it's quadratic residue. But what if it's not 1? Then what happens? Can it be a very wide number, or it can be controlled? So, what is your opinion? Can this be a very wide number, or this can be a specific number? And the answer is very simple. Answer is this. Then it is, this is it. In other words, it's either plus 1 or minus 1. Excuse me?
A to the H is congruent to -1?
Yes, right. So if it is not 1, then it is not wild. It is not wild. It is negative. Or whether it's 1 or negative 1. Not wild number. So let's check it. I will pause, but please check whether you understand the idea or not. If it is 1, it's quadratic residue, right? If it is not 1, then it's not residue. But what about the number itself? It is negative, right? It is negative. So let's go back and check it. I checked a few numbers with you, so let's return back and review. So take a look. 17 was a quadratic residue because of this fact, right? 17 was a quadratic residue. 18 also was a quadratic residue. But 112 chosen by you is not quadratic residue because it's not 1. Then take a look. With mod 937, 936 is congruent to what? Negative 1, right? Negative. So you cannot get y. Then I will show you the evidence. So I will do this mod for all the numbers. So let's do it. Power mod I running from So I will run all possible powers. Take a look. So I used, for instance, specific number, but now I is in the loop. So I will run it for all the numbers, but all you see is just 2 numbers. So let's run it. Power mod. So let's run it. Then take a look. The numbers that you see is not very broad. As you can see, either 1 or negative 1, right? 1 or negative 1. 936 is negative 1. Do you see it? 936 is negative 1. So 1 or negative 1, nothing else. In other words, no matter what number you use, if it is not 1, then it is negative 1, or negative 1 is the same as, in this case, 936. Do you see it? So all you see should be 1 or negative 1, nothing else. I'm giving you the proof, right? So let's do it. Let's prove it. I'm just showing you the calculational evidence or verification, but it's not proof. Proof is tougher, right? Proof is tougher than. So do you get the idea? If half power is 1, then it's quadratic. It's not 1, then non-residue. I know that. But what if it's not 1? Then what kind of number do we get? Negative, right? 1 or negative. And this is the crucial point in the next development. And in fact, without defining the symbol, I use the symbol. That symbol depends on this. In other words, people develop the symbol like this. A over P. This A over P is not general fraction, but it means whether it is 1 or negative 1. Coming from this result. So people develop this kind of symbol saying whether this half power is 1 or negative 1. If it is 1, then it's quadratic residue, right? If it's not 1, quadratic run residue, but the number is not very far away, it's negative. So it will be introduced in the next section. So this is very crucial, but let's prove this first. 9.2. In section 9.2, we will mention this. So take a look. A to the power of P minus 1 minus 1. What is this? You should know this fact. What is this? 0. By what theorem? Fermat, right? Fermat theorem, or generalized version, Fermat's theorem is like Euler's theorem, right? By Fermat or Euler's theorem, this is congruent to 0. Then this means A P minus 1 minus 1 is divided by P, right? Equivalent statement. This is equivalent to saying this number is divided by P. And if you factor this, then you get right? Just simple factoring gives us this. Because P is prime, P should divide this or this, right? Because P is prime. If P is not prime, then you may divide differently, right? Because P is prime, it should divide this or the other. So, what does this mean? P should divide this, or P should divide this. And if I write it using congruence instead of division, this is equivalent to saying what? A is congruent 1, right? This is equivalent to saying this. And then if we write it, so I can get this result, right? In other words, there are no other numbers than 1 and negative 1, right? Only two numbers are possible for a to the power of p minus 1 over 2. So if it is not 1, then by this fact, it is negative 1, right? So there are no other numbers possible. Then I will cover the examples later. Then I will overview the next section because we don't have enough time. I don't want to go into the new concept, but overview. Overview is the definition. If A is quadratic residue, then I want to say A over P is congruent, is equal to 1. If A is quadratic non-residue, then A over P is negative 1. And these will take only two possible values, 1 or negative 1. If it's 1, then it's quadratic residue. If it's not 1, then residue. So this symbol is called the Zandra symbol. And definition is right here. And all this come from Euler's criterion, right? Euler's criterion should give us 1 or negative 1. And this is it. So please check whether you can completely understand up to this point or not. Why do we care? Because it's not a very pleasant situation to describe everything by statement after statement, right? It's a good idea to use mathematical expression, right? So by just checking whether it's 1 or negative 1, we can check whether it's in residue or not. So from this point on, I will write down the number like this. So whether 17 is a quadratic residue or not can be answered by this. Assume that we calculated it and then found that it is 1. Then it is residue, right? If it is negative 1, then it's non-residue. Not practically, but theoretically, how can you do it? I showed you before. We can practically do it by doing this calculation. I will go up and then run it. So by doing this calculation, right? By doing this calculation, we can theoretically check whether it's quadratic residue or not. So by that calculation, it is 1 because 17 to the power of half is congruent to 1, right? 17 to the power of half is 1. So this is the idea behind the development of strange criterion after criterion up to section 3. Once we reach section 3, we will learn the property called the reciprocity. When we need to handle 17 over this small number over big number, then we can reverse it. We can reverse it like this with minor sign handling, right? Minor sign handling. So with minor sign handling, we can reverse it. Then with congruence 17, 937 is nothing but 2. Then suddenly we don't see any big number, right? We don't see any more big number, right? Then it is way easier to handle. So please browse the idea and check and ask questions if you don't. Then I will return back to section 1, then give you examples. Then let's go to section 1. So next time we will go into section 2 and then do the proofs of the theorems. But in section 1, textbook gave us plenty of examples, and then I will browse a few cases. First of all, P equals 13, then 2 to the power of, we did this before, right? Half, right? This is called half, right? 2 to the power of half can be calculated, and then it is 2 to the power of 6. 2 to the power of 6 is 64, right? 64 is congruent with 13, 12. 12 is congruent to what? Negative 1. 12 o'clock is negative 1 o'clock. So is 2 a quadratic residue or not? 2 is not quadratic residue. In short, because of this, 2, 13 is what? This number, right? Negative 1. 2 over 13, called the Legendre symbol, is negative 1. Because next time we will rely on this symbol instead of stating whether it's residue or not. Just rely on this symbol. It's a good idea to introduce symbol at this point, right? So this calculation gives us the clue about this number. And textbook also checked this kind of number. 3 is 3. In other words, in short, this is a question, right? This is a question. On the exam, I asked this, then some student divide 3 by 13 and wrote, oh, it should be equal to like 0.4 or 0.24, something. So it is a Legendre symbol, and then it is either 1 or negative 1. How can you check it? To check it, we use the fact that this is congruent to 3 to the power of half, right? This is called half. 3 to the power of half. And then 3 to the power of 6. And then 3 to the power of 6 can be calculated, and the textbook did it. And then it is 27 to the power of 2, right? 3 cubed is 27. But as you can see with 13, 27 is what? 27 is what? 1, right? And then 1. So, as you can see, 3 over 13 in the Legendre symbol gives us 1. What does this mean? It means quadratic residue, right? But you don't even have to say anything once you begin to use the symbol. Symbol equal to 1 means quadratic residue, right? So from this point on, in fact, from next time, when I use this symbol, the end result will tell you whether it's residue or not. 1 or negative 1 is the possibility. So if you have a question, ask me. If you don't, then I don't go over the next chapter section now. You can approach and ask.